Can you imagine keeping your mind sharp at 100 years old? A mind filled with a century of memories, yet nimble enough to learn something new. The human brain, this extraordinary universe of thought and feeling, is subject to the relentless passage of time. The question is not if our brains will age, but why this process seems so inevitable. Today, we'll uncover the 5 fundamental reasons why the brain's clock cannot be stopped, at least not yet. We'll journey into the microscopic world of neurons, witness oxidative damage, tangled proteins, ticking genetic clocks, chronic inflammation, and fading cellular engines. Join me, Alejandro Torres, as we seek to understand why we cannot halt the aging of the brain. Our story begins within the neurons, the cells that create our thoughts, memories, and every sensation we experience. Each neuron is a marvel, firing tirelessly for decades, orchestrating the symphony of our minds. But this relentless activity comes at a cost. Every breath and every thought produces free radicals, unstable molecules that damage cells, a byproduct of the very energy that keeps us alive. Picture these free radicals as microscopic bandits, stealing electrons and leaving a trail of destruction in their wake, invisible but relentless. Their main target, the delicate membranes of our neurons, crucial for sending signals and maintaining the brain's intricate network. Over time, these attacks create tiny wounds, like rust on a machine, making neurons less efficient and more vulnerable to further harm. The brain deploys antioxidants to neutralize free radicals, mounting a defense against this molecular onslaught. But with age, the damage outpaces repair. Neuronal membranes become scarred, hindering communication and slowing the flow of information between cells. Some free radicals reach the nucleus, damaging DNA and causing mutations that can alter the cell's fate. While cells have repair systems, decades of attacks let some errors slip through, accumulating over a lifetime. These errors disrupt vital proteins and can trigger cell death, apoptosis, a programmed self-destruction that removes damaged cells. This oxidative stress is a fundamental driver of aging, the price we pay for living, thinking, and simply being conscious. As years pass, neurons lose resilience, communication falters, and some cells are lost forever, never to be replaced. This is the first and perhaps most pervasive reason why the brain's youthful vigor fades and why mental sharpness can slip away. It's a slow, inexorable process written into the chemistry of life, unfolding quietly with every passing year. The battle is constant, and eventually, the molecular frontier is lost as defenses weaken. Oxidative damage is the silent force behind the brain's gradual decline, eroding function bit by bit. Even the best defenses can't hold out forever, and the balance tips toward decline. The result, slower thoughts, weaker memories, and a mind that feels the weight of time pressing down. This is the cost of being alive, the inevitable toll of existence. The brain's brilliance dims, not from a single blow, but from countless tiny wounds accumulated over a lifetime. And so, the clock keeps ticking, marking the slow passage of time within our minds. In the brain, proteins are the workers and messengers, tirelessly carrying out essential tasks to keep our minds sharp and our thoughts clear. But as we age, some of these proteins turn into saboteurs, disrupting the harmony within our neural environment. Beta amyloid and tau proteins, once helpful, start to misbehave, forming clumps and tangles that choke brain cells and interfere with their normal function. Beta amyloid fragments, which are normally cleared away by the brain's cleaning systems, begin to stick together, forming stubborn amyloid plaques between neurons. These plaques block communication, trigger inflammation, and add to oxidative stress, further damaging delicate brain tissue and accelerating the aging process. Inside neurons, tau proteins act as stabilizers for the cell's internal transport highways, ensuring nutrients and signals reach their destinations. But with aging, these tau proteins detach and twist into tangles, losing their ability to support the neuron's structure. These neurofibrillary tangles collapse the cell's internal transport, starving the neuron from within. The result: disrupted communication, lost nutrients, and eventual cell death, a slow unraveling of the brain's intricate network. Under the microscope, an aged brain is littered with plaques and tangles, a wasteland compared to the dense forest of youth, where connections once thrived. This buildup of protein junk is a hallmark of cognitive decline, marking the transition from healthy aging to disease. The brain's intricate network becomes clogged, slowing thought and memory, making even simple tasks a challenge. These protein aggregates are not just signs of aging, they actively drive it, spreading damage from cell to cell. The more they accumulate, the harder it is for the brain to function, leading to a gradual decline in mental abilities. Clearing them remains one of science's greatest challenges, as researchers race to find solutions. For now, they stand as barriers to a youthful mind, blocking the pathways that once made learning and memory effortless. The city of the brain, once bustling, becomes gridlocked, its roads and subways choked with debris. Communication falters, and the lights begin to dim, signaling the fading of mental clarity. This is the second reason the brain's clock cannot be stopped. Time and protein aggregates march on together. Protein aggregates are the silent saboteurs of our mental city. Their legacy is confusion, forgetfulness, and decline, robbing people of their memories and sense of self. The battle against them is ongoing, with scientists and doctors searching for new ways to protect the brain. But for now, they are winning, overwhelming the brain's defenses, and the brain pays the price, as the weight of these aggregates brings about the slow erosion of our most vital organ. Our cells' remarkable ability to heal and renew themselves depends on their capacity to divide, a process that is vital for growth, repair, and survival. But this power isn't endless. It comes with a built-in limit. At the very tips of our chromosomes are telomeres, protective caps made of repeating DNA sequences. These act as guardians, shielding our genetic material, but they shorten with every cell division. Think of telomeres as the plastic tips on shoelaces, preventing the ends from fraying and keeping everything intact. Each time a cell divides, its telomeres get a little shorter, acting as a biological clock that counts down with every replication. In the brain, this process is especially crucial for neural stem cells, reservoirs that give rise to new neurons and help maintain brain health. As we age, these stem cells divide more slowly, and their telomeres continue to shrink, gradually reducing their ability to replenish lost or damaged neurons. Eventually, telomeres become too short to protect the DNA, and the cell retires. Unable to divide further, it enters a state of permanent rest. The brain's supply of new neurons dwindles, especially in regions like the hippocampus, which is vital for memory, learning, and emotional regulation. The result: less plasticity, slower learning, and a reduced ability to repair itself after injury or stress. There's an enzyme called telomerase that can rebuild telomeres, restoring their length. But in adult brain cells, it remains mostly inactive. This inactivity is a safety measure against cancer, since uncontrolled cell division can be dangerous, but it also limits the brain's regenerative potential. The brain's ability to renew itself is finite, set by the length of its telomeres, a biological limit written into our very cells. As the clock winds down, the brain's capacity for growth and repair fades, and the effects of aging become more pronounced. The genetic timer keeps ticking, quietly limiting longevity and renewal from within, no matter how healthy our lifestyle. This is the third reason the brain cannot escape aging, a fundamental barrier locked deep in our biology. The loss of renewal is written into our DNA, encoded in the very sequences that make us who we are. The brain's future is shaped by the slow erosion of its own foundations, and the countdown continues, ticking away at the core of our being. The brain's immune system, led by microglia, is its vigilant protector. In youth, microglia clean up debris and defend neurons. But with age, this system becomes overactive, shifting from guardian to source of chronic inflammation. Microglia, constantly triggered by accumulated damage, enter a state of perpetual activation. Instead of brief targeted responses, they release inflammatory chemicals non-stop. This chronic inflammation damages neurons, increases oxidative stress, and disrupts synapses. The brain's own defenders become part of the problem, fueling a vicious cycle of damage. The blood-brain barrier weakens, letting in more inflammatory agents. The brain, once a sanctuary, becomes a battleground. Chronic neuroinflammation is now seen as a key factor in nearly all age-related brain diseases. The cycle feeds itself, degrading neural networks and eroding cognitive abilities. The protectors become destroyers, and the brain suffers the consequences. This is the fourth reason the brain's clock keeps ticking. The brain is an energy-hungry organ powered by billions of mitochondria, its cellular engines. These mitochondria convert food and oxygen into ATP, the energy currency every neuron needs. In youth, mitochondria are efficient, fueling sharp thinking and quick learning. But their own DNA sits near the site of energy production, exposed to constant free radical damage. Over time, mitochondrial DNA accumulates mutations, making these engines less efficient. Damaged mitochondria produce less energy and more harmful byproducts, accelerating their own decline. As neurons lose power, communication weakens, repair slows, and vulnerability increases. The city of the brain experiences rolling blackouts, slower thoughts, fatigue, and cognitive decline. Eventually, energy deficits trigger cell death, shrinking the brain's network. Mitochondrial dysfunction is a central feature of brain aging. The lights dim, and the mind slows. This is the fifth reason the brain cannot escape time's grip. The loss of energy is the final blow to a once vibrant mind. The decline is inevitable, written in every cell. The brain's brilliance fades as its engines fail. We've explored the 5 forces that drive brain aging: oxidative damage, protein aggregates, telomere shortening, chronic inflammation, and mitochondrial decline. Each of these factors plays a unique role in shaping how our brains change over time. These intertwined processes form the biological foundation of why we cannot yet stop the brain's clock, no matter how advanced our technology becomes. But understanding them reveals the brain's incredible resilience and points the way for future science, inspiring new hope for breakthroughs. The challenge is immense, but so is our curiosity and determination to keep searching for answers. Our brain is our legacy, even as time leaves its mark and memories become our most precious treasures. If you found this journey fascinating, subscribe for more explorations into the wonders of science and the mysteries of the mind. Until next time, stay curious and keep exploring.